Alright, so section 8.4 is on something called Bayes' Theorem. Now that's really just going to be the title of this chapter for us, and we're not really going to discuss the formula for the theorem. Instead, we're just going to talk about methods for applying it. But let's remember what we covered last time, or an example we covered last time. We talked about the presidential elections, and we saw that we saw Gingrich, Romney, and Kane. We saw that Newt Gingrich, we constructed this probability tree, and the probability that Newt Gingrich runs for the president and loses is 2, 3, 1. The probability that Mitt Romney runs for the president and loses is 0.175. And the probability that Kane runs for president, Herman Cain runs and loses is 0.1311. Now, altogether, this means that the probability that a Republican loses is just the sum of these three things, and that adds up to 0.5371. But let's pretend that somehow you travel to the future, I don't know, and you find out that indeed the Republican candidate lost. Then you can go back and say, well, how likely is it that it was Gingrich or Romney or Kane? And so here's our question. Given or assuming that the Republican loses, what is the probability it was, Gingrich, Romney, or Kane? Okay, well, we've already figured out to, for example, to say, given that they lost, what's the probability that the candidate was Gingrich? We need to do what is the probability that it was Gingrich and he lost divided by the probability that he lost. Well, we already had that information coming from our probability tree. In our probability tree, we had that the probability that it was Gingrich and he lost was 0.231. That was at the end of his branch, divided by 0.5371, which gives us 0.43. And let's compare this to the probability that Gingrich actually is the nominee, which is 0.42. So if they lose, it's actually more likely that he was the nominee than just overall. If we look at Romney, the probability that it's Romney, given that the Republican loses, is the probability of Romney and losing divided by the probability of losing, which is 0.175 divided by 0.5371, which is 0.326. And I'd like you to compare this to the probability that he's actually the nominee, which is 0.35. So the probability that he's the nominee, given that they lose, is actually a fair bit smaller than the probability that he's the nominee. Again, this suggests that he really should be the nominee. Similarly, you could do the same analysis for Kane, and for him you get 0.244, which compared to the probability that he is actually the candidate, 0.23, that's a fair bit more. If the Republicans go for Kane, they're probably going to lose. So that's the deal. But what did we really do here? We started with conditional probabilities, probability of some event given some other events, Fi. And here we're assuming that the Fi formed a partition of our sample space, by which I mean that they are all mutually exclusive, F1, F2, F3, they're mutually exclusive, but their union is the whole sample space. So Fi intersect Fj is empty if they're not the same, and the union of F1, F2, all the way up to Fn is S. So that's what it means to be a partition. So we're given a bunch of conditional probabilities of some event given some sort of partition. In our case, it was Gingrich, Romney, and Kane. And then we started with these conditional probabilities and instead wanted to end up with the conditional probabilities of each of the things in the partition given the result. So for example, we wanted to find the probability that a particular candidate was the nominee given that the candidate actually, or the nominee actually lost. So this is the idea behind Bayes' theorem. And so the picture is sort of this. Let me just simplify it down to three cases. So we've got three things, F1, F2, F3, and each of them goes off to E and something else, maybe some other things. All I really care about is E. So we have the probability of F1 here, the probability of F2 here, the probability of F3 here, and we have a bunch of conditional probabilities here. The probability of E given F1, the probability of E given F2, and the probability of E given F3. Now let's say I want to find out the probability of F1 given E. What I do is this. I take the following. I multiply all probabilities, that going from F1 to E, and let me highlight what I mean by that. That means that I take the probabilities for going from F1 to E, I multiply these probabilities, and I put that quantity on top. Okay, so that's the green, highlighted in green. And then I divide that by the sum of the products of all probabilities on branches going to E. So if I look at, if I want to highlight this, here's another way that goes to E, and here's another way that goes to E, and I multiply these probabilities together, and I add them up. I've also got to consider the one branch that I got from the green part, so I add the green, the blue, and together, and I divide the green by the sum of the greens and the blues. So I multiply these probabilities together, that gives me the top, etc. So let's go through a couple more examples of this. One common example here is disease testing. A lot of fun, but it's good to, this is a really good source of examples. Let's take disease testing. Let's say that 99.9% of a population doesn't have a given disease, and 0.1% does. So I'll call the event that they have the disease D. The event that they don't have the disease will be D prime. Now this is going to be acting as our partition. Now there's some test for the disease, and it satisfies this. People with the disease test positive 99% of the time, and people who don't have the disease test negative 95% of the time. Well, that seems pretty good, you know. 99% of the time the test is right for people who have it, and 95% of the time it's right for people who don't have it. But let's really ask the question that you would really be interested in if you're getting tested for this disease. What you really care about is what is the probability I have the disease if I test positive. And you should go back and look. I said, given that you have the disease, the probability you test positive is 99%. This is saying things backwards. Given that you test positive, what's the probability you have the disease? So this is different. So let's write out all of the information. What I want here is the probability I have the disease given that I tested positive. What information have we been given? The probability that you have the disease is 0.01. The probability that you don't have the disease is 0.001. The probability you don't have the disease is 0.999. The probability that you test positive given that you have the disease is 0.99, which means that the probability that you test negative given that you have the disease is 1%, 0.01. And the probability you test positive if you don't have the disease is 0.05, because the probability that you test negative given that you don't have the disease is 0.95. Alright, let's take all of this information and put it together into a probability tree. Now the given, the partition, is having the disease or not having the disease. After that, we're given probabilities that you test positive or negative. So again, 0.001 is the probability you have the disease, 0.99 is the probability that you test positive if you have it, and 0.01 is the probability you test negative if you have it. 0.999 is the probability that you don't have the disease, 0.05 is the probability you test positive, and 0.95 is the probability that you test negative. So what we are really interested in, though, is the probability that you have the disease given that you test positive. Well, the formula says that we want to first take all of the probabilities that lead up to you testing positive that go through you having the disease, and that's just this one branch. And you multiply these probabilities together. So the numerator of the fraction we're looking at is going to be 0.001 times 0.99. That's literally the probability that you have the disease and you test positive. But now we want to add on top of that both of the branches that go to positive. We want to add the one that we've already considered and the branch that corresponds to not having the disease but testing positive. So that means that we are adding together 0.001 times 0.99 plus 0.999 times 0.05. Now, I didn't bother writing down all the steps here. I just went ahead and plugged into my computer. What you get is 0.0194. Whoa, that's kind of weird. 1.94% of the time you test positive, you don't have the disease. That's weird. The test seemed like it was pretty good, but no, it's not so good when you test positive. If you test positive, it's actually just scaring you. You probably don't have the disease given that you test positive. And that's because most people don't have the disease, and the error rate of people who don't have the disease testing positive is fairly high. 5% of the people who don't have the disease do test positive. So the most people who test positive are coming from the non-disease part. You're probably also interested in what the probability that you don't have the disease, given that you tested negative, is. And hopefully, you can go back and write down that tree diagram from before. But what this turns out to be is the probability that you test negative, given that you don't have the disease, times the probability that you don't have the disease, divided by the same thing, plus the probability that you test negative, but you do have the disease, times the probability that you do have the disease. And this works out to 0.9999 something. So this is actually good. 99.99% of the time, a negative result is correct. Okay, so that's nice. But that's good. So what is the value of this sort of test? Well, if the test is, say, cheap, it can be a good initial screening for the disease, because it will take most people who don't have the disease and immediately say you don't have the disease. However, if it does turn up positive, if it turns up, that's supposed to be a plus, more testing would be needed because you still probably don't have the disease. Okay, so just something to think about. And so when you're looking at, if you're ever, for some reason, getting tested for a disease, what you're really interested in is, if I test positive, what's the probability I have the disease? Not the other way around. Not if I have the disease, what's the probability I test positive? That's not what you're interested in. You're interested in, here's the information I have, do I have this disease? Okay, let's do one final example, and this is an example I do fairly often. It's looking at poverty in New York City, and I'm just going to go straight and draw the tree diagram that corresponds to this. So let's look at the 5 boroughs of New York. I should really try to draw this a little bit bigger. Let me see if I can do that. No, in fact, I'll draw kind of like this. Okay, so we've got the Bronx, we've got Brooklyn, we've got Manhattan, we've got Queens, we've got Staten Island. And here's the percent of the entire population that each of these boroughs represents. The Bronx is 16.6% of the population, Brooklyn is very populous. It is 30.6% of the population. Manhattan is not so populous. It's 19.4% of the population. Queens is close to and catching up on Brooklyn. It's 27.5% of the population, but it's the biggest borough by far, so it's it really should be more populous than Brooklyn in a sense, but you know their subway access is worse, so I suppose that's a reason why people don't necessarily like to live there. Anyways, in Staten Island is only 5.9% of the New York population. Now let's look at the poverty rate of each of these boroughs. I'm only going to draw the branch corresponding to poverty. P here stands for poverty, namely the percentage of each the people in each borough who live in poverty. The other half would be people who don't live in poverty, and the two probabilities for each of these branches would add up to 1, so you can figure that out. But in the Bronx, 27.1% of the people live in poverty. In Brooklyn, 21.9% live in poverty. In Manhattan, 17.6% live in poverty. In Queens, 12% live in poverty. And in Staten Island, 9.8% live in poverty. So these are conditional probabilities that say, what's the probability that you live in poverty given that you live in the Bronx, etc. But you might be interested in saying, well, hey, wait a minute, what's the probability that you live in the Bronx given that you live in poverty? It's only 16.6% of the population of New York, but maybe it has a fairly high percentage of the population that lives in poverty because it has the highest percentage of its residents living in poverty. Well, you can use this Bayes Theorem thing to do this. You would take the probability that you live in the Bronx, given that you live in poverty, is going to be the product across that first branch, which is 0.166 times 0.271, divided by the products off to poverty, or the products along the branches that end in poverty along the rest of the branches. So the one for the Bronx, now I'm not going to write them all out, but all the way on down to the one for Staten Island, which is 0.059, which is the percent of the population, times of New York's population, times 0.098, which is the percentage of the population of Staten Island that lives in poverty. Now this gives us 0.045, which says that 4.5% of the city's population live in the Bronx and live in poverty, divided by 0.185, which says that 18.5% of the city's population lives in poverty. And when you take this quotient, you get 24.3. So 24.3% of the city's poverty population lives in the Bronx. And compare this to the fact that only 16.6% of the total population lives there. So this shows something about the demographics of New York City at the very least, and depending on how you want to interpret it, could mean bigger things to you. I don't know. All right, conditional probability Bayes theorem.